if whenever because the image of this gamma is precisely C1, the union of C1 and C2. Okay, it is easy to see that the image of our this gamma is the union of C1 and C2. So if we can prove that once the gap of P is very small, then the total range of the equivalent polygonal of gamma, which is under the partition P, is very close to the sum of the range of C1 and C2, then we are done. But the inscribed polygonal of the partition P of gamma under the partition P is the sum of this the sum of the length of the segment joining the points described in this picture. The problem is that this sum has nothing to do with the corresponding partition of C1 and C2, because partition of C1 and C2 must contain a point, the point B here. This is the point corresponding to B. That is also gamma 1B and also gamma 2B. Okay, we need to add this point. The trick is that when you connect the point, connect the point here. So this is Tj minus 1, this is Tj. We connect them. Fortunately, the sum of these two segments is greater than the this is B, not Tj. Tj is here. Oh no. This is B. This is Tj. Okay, the sum of Tj minus 1 and B and B to Tj is greater than the segment gamma Tj minus 1 and gamma Tj. Okay, so this is the tricky part of the proof. Now we construct the curve gamma, joining the two curve gamma 1 and gamma 2. We obtain a parametrization C gamma of our curve C1 union C2, and then if P is a partition of this interval, we must assume that B belongs to one subinterval Tj minus 1 Tj. Then we consider the range of the inscribed polygonal of gamma, which respect this partition P. We consider the difference of this. The range of the inscribed polygonal, which the sum of the range of the two curves, two paths. This, by definition, this is I from 1 to m. Gamma Ti minus gamma Ti minus 1. This is the segment, the range of the S segment, minus LC1 plus LC2. And this sum can be written by sigma I from 1 to j minus 1 and sigma I from j to m. I from 1 to j minus 1 corresponding to those endpoints containing in the curve C1. Okay, and I from j to m corresponding to the endpoints on C2. So so the part here, the part around B is omitted. Okay, so we what color I will use? Red. So this the length of this inscribed polygonal is the length of this inscribed polygonal. Go here and then tj minus 1, then go to tj, then continue, finally end up at the endpoint of C2. So this point allow B have no contribution to our total length. But to write the length of C1 and C2, we need to count the part along B. We need to count these two parts. Okay? We need to join the tj minus 1 to B, then B to tj. We need to join this. So what shall we do? Okay? What shall we do? We insert the term tj, b, insert the term b. So we write this estimate to be j minus 1, I from 1 to j minus 1, gamma ti minus 1. Then we add a term gamma 1b minus gamma 1. This is gamma 1. I will add later. Gamma 1 tj minus 1. Then subtract the length of Cj, and then plus j from I from j to m, gamma ti minus gamma ti minus 1, then plus gamma 2b, gamma 2tj minus gamma 2b, then subtract the length of C2. We add the two terms. We add these two terms. These two terms will be subtracted later. But the space is too little to write more. So I write it in the next page. Then the two terms we added is gamma 1b minus gamma 1 tj minus 1 plus gamma 2 tj minus gamma 2b, right? So let's go back. We want to estimate this term. Because of the above reason, we need to contend those terms involving B for the computation of the length of C1 and C2. But so we add this term. We add this term to including the segment to B, and also this term also to including the segment in C2 connecting to B. Okay, but adding these two terms, we need to subtract them. Subtract here, and then we use the property of absolute value. We the total absolute value will not greater than absolute value of several parts. So we add absolute value here and here. Also, the last part here. This last part already non-negative, therefore absolute value is there itself. Okay, and adding this absolute value, this will not be equality. This will be less than or equal to. Okay, so we get this result. Now we have a look on this. For I from 1 to j minus 1, the ti lies in the because b is less than tj. So for I less than j, For I less than j, this ti less in AB. Ti less in AB, gamma ti is gamma 1 ti. Because for t in AB, our gamma t is gamma 1 t. Okay, so for this sum, for the summation here, the gamma ti is gamma 1 ti. Therefore, we can gamma 1 here. Okay. Similarly, for I greater than j, I greater than or equal to j, because b is less than or equal to tj. So for I greater than or equal to tj, the ti will not less than b. Therefore, the ti less in the interval bc. So in the interval bc, our gamma t is gamma 2. Okay, in the interval bc, our gamma t is gamma 2. So in the second sum, this is gamma 2. Okay, now let's have a look on the first sum. In the first sum, including the term we added for b, what's this? This is precisely the total length of the inscribed polygonal of gamma 1, of C1. So, because gamma 1 is rectifiable, it has a length LC1. So, and our partition P, the gap of our partition P, when the gap of our partition P is less than delta, this partition of the union less than delta, this gives a partition of C1 and C2, which is gap less than delta also. So therefore the length of the inscribed polygonal of C1 will very close to LC1. So the first term is less than epsilon. Or I will write in the next page. The first summation from j to 1, the absolute value of the first summation from 1 to j minus 1 will not greater than or I will write one more step. The first term is gamma 1. Not easy to write. I will not write. The first term will not greater than epsilon. No. Maybe. Okay. The first term is precisely L gamma 1 P1 minus LC1. Where P1 is P intersect with AB, then adding the point B inside. This is the partition of AB. How to understand this? So this is our interval A, B, C. The blue point are the point in the partition P of the interval AC. Then we take the point in the interval AB. This is what this intersection means. But this only gives us these points. This point is not a partition. This point do not consist of a partition of AB, because as a partition of the interval AB, you need to contain the point B. Therefore, we included the point B. So this red dots give a partition of AB. This is our P1. So in our this sum, the red box part in this sum is precisely the total length of the inscribed polygonal of the curve C1, determined by the partition P1, defined here. Okay. Similarly, the second term in this sum, the second term in this sum is also the length of the inscribed polygonal of our curve C2 corresponding to a partition P2 of the curve C2. What's C2? P2. Sorry, P2. So I write the result first. Plus L gamma 2 P2 minus L C2. So what's P2? P2 is this. P intersect with BC. Then also we need to add the point B. In this picture, we take the point of the partition P containing in the interval BC, but this might not be a partition of the interval BC, but adding the point B, we obtain the partition of BC. This is our P2. Okay, these two absolute value are precisely the two terms in the last two lines in this page. Okay, now we copy the term we need. We added in the previous estimate, so we also need to copy this. So the length of the inscribed polygonal of our curve gamma, which leads back to the partition P, subtracting LC1 plus LC2, the absolute value will not greater than the sum of these three parts. Each part less than epsilon. The first part is the length of the inscribed polygonal of gamma 1 under the partition P1, which is very close to the length of C1. Similarly, the second part is also less than epsilon. The third part, the third line, is also less than epsilon, because this is the delta we chosen, so that this is true. Now the t here is tj minus 1. The distance from tj minus 1 to b is less than delta. So tj minus 1 can be taken as the t here. Similarly, s is tj. S is tj. The distance from s to b is also less than delta. So the sum of these two is less than epsilon. Applying this result, this part is also less than epsilon. So in total, this is 3 epsilon. So this means for any epsilon positive, we can determine a delta using the rectifiability of gamma 1 and gamma 2, and as well as the uniform continuity of gamma 1 and gamma 2, we determine a delta here. Which this delta, if the partition P of the interval AC, the gap is less than delta, then the corresponding length of the inscribed polygonal will very close to the length of C1, the sum of the length of C1 and C2. So this proves that C is gamma. Gamma has length LC1 plus LC2. But gamma is a parametrization of the union curve C1 union C2. That is, C1 C2 is the length of C1 plus the length of C2. So this completes the proof of this theorem, this lemma. This will be useful later